All right, so our project is about optimizing pessimism in dynamic treatment regimes based on a Bayesian learning approach. And here is the outline of our presentation. And we will first talk about the motivations of our project. And our project is focused on the application of the dynamic treatment regimes, where most existing methods rely on a positivity assumption in the offline data for finding the optimal policy. And this can be also regarded as a problem of the offline reinforcement learning, where many algorithms also rely on a crucial coverage assumption, which requires the offline data distribution to provide a good coverage over the state action distribution induced by all candidate policies. Therefore, the pessimism principle has been designed to discourage recommending actions that are less explored conditioning on the state. And there are two kinds of methods for the pessimism principle algorithms, which are model-based algorithm, and this basically penalize the reward or transition function. While another one is the model-free algorithm, which focused on learning a conservative Q function. However, most of these solutions either require a well-specified parametric model, which can suffer from the model misspecification in practice, or they just rely on a K hyperparameter to codify the degree of pessimism. And this kind of solutions can be sensitive to a choice of hyperparameters in practice, which can cause some troubles. Therefore, we come up with a pessimism-based Bayesian learning approach, which integrates the idea of pessimism principle, Thompson sampling, and also the Bayesian machine learning approach. And compared with the traditional or existing pessimism principle algorithms, our method doesn't require any additional tuning of the degree of pessimism. As a result, it can help us to achieve more consistent and competitive performance in practice. In addition, because of the incorporation of the pessimism principle, our method can also achieve a better decision rule when the coverage condition is seriously violated. And in addition, our proposed method can also work with a wide range of different Bayesian machine learning models, including the Bayesian linear basis model or the Bayesian neural network, which we will talk about a little bit later. And this can help to make our model to be powerful to capture all the complex signals in reality. And finally, our proposed method is efficient and scalable to large data sets, because we also use the approach of variational inference to approximate the true posterior distribution of the Bayesian model. And this is computationally efficient in practice. And here is a quick recap of the Bayesian machine learning model. And in our paper, we basically consider two kinds of Bayesian models. Well, the first one is the Bayesian linear basis model, which is just a general extension of the classic Bayesian linear model. And another is the Bayesian neural network, which imposes the prior distribution for the model weights of the neural network. Then the exact posterior distribution of the model weights can be just approximated by using the variational inference through minimizing the KL divergence. And for the pessimism principle, Jin proposed a method called PEVI, which tries to learn the uncertainty quantifier gamma of the Q function. And when they try to construct the policy, instead of using the original Q function, they choose to use the lower bound of the Q function, which is basically the difference between the Q function and the uncertainty quantifier gamma. However, in practice, such uncertainty quantifier is hard to calculate by using a general formula. And in their paper, they basically just consider a specific case of a linear structure model. So this is a quite constrained parametric model in the paper. And here is the general procedure of our proposed pessimism-based Bayesian learning model. And we consider we start to consider the simple case of the offline contextual bandit. And we get this observed data set consists of the state, action, and the rewards. And the first step is to fit a Bayesian machine learning model on this data set. For example, we can use Bayesian linear basis model or using the Bayesian neural network. And because of the Bayesian model, we can construct the posterior distribution or just compute the posterior distribution of the Bayesian model. And we can draw a bunch of samples according to the posterior distribution and also construct the credible interval over here according to the significance level we have specified for the algorithm. And then we can pick an element of the model weight from this credible set to minimize the Q function. And this will generate the uniform lower bound for our Q function. And we will use this uniform lower bound to construct the estimated optimal policy for this problem. And our method can be also generalized to the case of multiple stage dynamic treatment regimes, where we have the data for a lot of stages. And to apply our method for this kind of case, we can just iteratively to apply our previous algorithm to each stage of this data set. So for example, if we focus on the last stage K, we can just apply our previous algorithm to derive the lower confidence bound of the Q function at stage K. And then we can construct the saddle reward according to this uniform lower bound. And this saddle reward will be used for the previous stage K-1. And we can just go back to the previous stage and repeat everything again and over again until the first stage. And this will generate a sequence of actions for each stage according to each lower bound. And finally, it will produce the estimated optimal policy for this multiple stage dynamic treatment regimes problem. And we also established the theoretical guarantee for our proposed method. So under the regularity conditions, as the sample size and the number of samples by using the posterior sampling goes to infinity, we can show that the average regret can be upper bounded by using this estimation error of the Q function. And note that for the estimation error here, it is only concerned with the optimal policy, instead of the uniform estimation error at each action. That means our proposed method doesn't require any additional assumptions for the full coverage of the whole dataset. In addition, if we consider the specific case of the Bayesian linear basis model, such upper bound can be written into this formula over here, which means that the average regret can converge in the rate of 1 over square root n in this specific case of Bayesian linear basis model. And we also implement some simulations to demonstrate the superior performance of our proposed method. And for here, we consider the single stage contextual bandit as a demonstration over here, and we use different signals, including the linear and nonlinear structures. And we also have more simulation results in the appendix of our paper for multiple stages, if you are interested to take a look at. And for here, we try to compare our proposed method with the Perry method of Jin's paper and also the standard Q-learning method. And for our proposed method, we consider both Bayesian linear basis model and also the Bayesian neural network. And for the standard Q-learning method, we use this notation non-pessimistic by using the blue cover here to represent the standard Q-learning method. And for here, different value of small c here represent the different hyperparameter, the different choice of the hyperparameter for the Pavin method when we implement the simulations. And for here, to generate the action sequence, we use epsilon gradient method by considering different values of epsilon over here. And from all the plots here, we can see that when epsilon is larger or equal to 0.75, our method can outperform the standard Q-learning method and achieve comparable results with PEVI method. And when epsilon equal to 0.5, our method can have very similar performance compared with the standard Q-learning. But if you take a look at the PEVI method, we can see that the PEVI method can easily over-penalize the Q function, which leads to a very large regret in this case. But anyway, in all of these cases, our proposed method can achieve a much better or comparable performance with the other method. And that demonstrates the superior performance of our proposed method. And we also consider real data analysis by using the MIMIC3 dataset. And here is a heat map for the frequencies of the actions generated by the Bayesian policy, the learned policy by our proposed method, and also the standard Q-learning. And from the heat map here, we can see that our proposed method can produce the policies that is more consistent with the physician's decision. But for the non-pessimistic pessimism approach or the standard Q-learning approach, it can produce some result that can be very far away from the physician's decision. And as a byproduct, we also evaluate our performance, the performance of our proposed method by using the offline policy evaluation as an actual criteria. And we compare our proposed method with standard Q-learning and also conservative Q-learning method. And from the result here, we can see that our proposed method can achieve the highest average reward compared with all the other methods. And here is a brief discussion of our project. So we basically developed a novel pessimism-based Bayesian learning approach for the offline optimal DTRs. And we propose to combine the pessimism principle with Thompson sampling and Bayesian machine learning to optimize the degree of pessimism. And we also conduct extensive experiments to illustrate the superior performance of our proposed method, and we also develop some theoretical guarantee for our proposed method. And this is a presentation for our paper, and thanks a lot for listening.